My name is Bryce Adelstein Lelbach. I'm NVIDIA's architect for HPC programming models. I'm also the chair of the U.S. Committee for Programming Language Standards and the International C++ Committee's Library Evolution Group. Today, I'm going to tell you about the NVIDIA C Standard Library. For over a decade, we've been expanding what GPUs can do. We want all the familiar programming facilities and abstractions to just work on GPUs. This is essential to enabling developers to adopt GPUs. If they're easier to program, you're more likely to use them. Standard C++ consists of two equally important components, the core language and the standard library. The ISO C++ standard is 1,800 pages long. 1,100 pages of that is the standard library. C++ without a standard library is severely diminished. Other C++ standard library implementations can only be used on CPUs. We wanted a C++ standard library that can be used everywhere, on CPUs and GPUs. So we built one, the C++ standard library for your entire system. It's open source and available today on GitHub, in the NVIDIA HPC SDK, and in the CUDA toolkit. In 2019, we launched Libcu, an opt-in, heterogeneous C++ standard library subset for NVCC. Libcu is distinct from your host compiler's standard library. It doesn't provide the standard library facilities in the std namespace, because with NVCC, we don't control that namespace. The host compiler's standard library does. Unfortunately, those std facilities won't work on GPUs with NVCC. Instead, Libcu provides heterogeneous versions of select C++ standard library facilities in the CUDA std namespace. It also provides modern C++ abstractions for the CUDA platform in the CUDA namespace. Libcu is not a complete standard library today. Each release adds more features. We've focused on two high-priority areas: facilities that need a specialized CUDA implementation, like concurrency primitives, clocks, and syscalls, and essential facilities that everyone is forced to re-implement, like type traits and tuple. Now, we're taking the NVIDIA C++ standard library one step further and bringing it to the NVIDIA HPC compiler, NVC++. The NVIDIA HPC compiler is a single interoperable toolchain that supports all major intranode HPC programming paradigms: 4 programming models, standard parallelism, CUDA, OpenECC, and OpenMP, 3 programming languages, C++, C, and Fortran, 2 targets, multi-core CPUs and NVIDIA GPUs. It's one compiler that you can use to program your entire system. If you want to learn more about NVC++, watch my other GTC talk, Inside NVC++ and NV Fortran. Earlier this week, we announced that CUDA C++ is coming to NVC++ in the near future. NVCC and NVC++ have completely different compilation models. NVCC uses a split compilation model where an external host compiler is paired with a device compiler. NVCC splits code into target-specific variants during preprocessing before compilation even begins. The code is independently preprocessed, parsed, analyzed, and optimized multiple times, once for each target. While NVCC has control over the device compilation, host compilation is controlled by the host compiler that NVCC is paired with. NVCC must work within the parameters and constraints of what that host compiler supports. Unlike NVCC, NVC++ uses a unified heterogeneous compilation model. There's no separate host compiler and device compiler. There's just one compiler, NVC++, a unified stack that orchestrates everything. In the unified model, we preprocess once, we parse once, we build one unified abstract syntax tree, we build one unified intermediate representation, we analyze it once, and we perform high-level optimizations on it once, and only then do we split into code gen for specific targets. Unified compilation offers many benefits for NVC++. It's more efficient. We parse, analyze, and optimize once instead of multiple times. A single canonical representation of code provides greater visibility, analysis, interoperability, and control across host and device code. This means increased robustness, better diagnostics, better language support, and more heterogeneous features. And because we control the entire toolchain in NVC++, including the host toolchain, we can provide our own complete and standalone standard library. And that is exactly what we are going to do. The next generation NVIDIA C standard library, Libnv++, is coming to NVC++ in the near future. Libnv++ is not a subset. It's a complete heterogeneous standard library for all of the programming models that NVC++ supports. While Libcu is distinct from your host standard library in STUD, Libnv++ is your standard library. There's no host compiler and no separate host standard library. It's a complete standard library implementation that provides all of the facilities in STUD. And unlike with NVCC, many of those facilities in STUD are heterogeneous and can be used on the GPU. Libnv++ also provides CUDA STUD for compatibility with NVCC and the extensions in the CUDA namespace. While Libcu++ is just a small subset of the standard library, Libnv++ is a complete C++ standard library. Everything in STUD is available on host, and most things will work on device. It's easier for us to deliver heterogeneous standard library features in NVC++. We control the entire toolchain. We only have to support one compiler frontend. And NVC++ execution space inference means we don't have to add host and device everywhere. To learn more about that, check out my Inside NVC++ and NV-Fortran GTC talk. To summarize, a homogeneous ISO C++ standard library like GCCs or MSVCs provides an implementation of STUD that only works in host code. Libcu++ provides an implementation of CUDA and CUDA STUD that works in host and device code, but it doesn't provide any part of STUD. It's available today in NVCC for CUDA C++. Libnv++ provides an implementation of STUD, CUDA, and CUDA STUD that works in both host and device code. It will be available in NVC++ soon for C++ standard parallelism, C++ OpenACC, C++ OpenMP, and CUDA C++. Today, NVC++ uses GCC's libstud C++ as a standard library, which only works in host code but is ABI compatible with code built with GCC. Libnv++ is heterogeneous, but it's not ABI compatible with GCC. In the future, you'll be able to choose which standard library you want to use with NVC++, either libstud C++ or libnv++. You'll be able to try out Libnv++ in an upcoming release of NVC++. Now, let's dive into the contents and roadmap of the NVIDIA C++ standard library. Our first release in 2019 introduced heterogeneous atomics and type traits. The 1.1 release introduced a number of scalable standard C++ concurrency primitives, atomics wait and notify API, barriers, latches, and semaphores. It also introduced CUDA memcopy async, an extension for asynchronous data movement. Heterogeneous standard C++ clocks were also added. In 1.2, we introduced CUDA pipeline, an extension for coordinating asynchronous data movement. In 1.3, we added tuple. 1.4 brought complex, byte, and chrono dates and calendars. Let's start by looking at one of our marquee features, atomics. There are two versions of atomics in the NVIDIA C Standard Library. First, there's our extended version, CUDA Atomic. Standard C++ presents a view that the cost to synchronize threads is uniform and low. In practice, C++ on NVIDIA GPUs is different. The overhead is low among threads within a block and high across arbitrary threads in the system. To bridge these two realities, the NVIDIA C++ Standard Library introduces extended versions of familiar standard C++ concurrency primitives in the CUDA namespace. These extended primitives take an optional thread scope parameter. Aside from the thread scope parameter, they have the same syntax and semantics as their standard C++ counterparts. A thread scope specifies the kind of threads that can synchronize with each other using a primitive such as an atomic or a barrier. Thread scope system indicates that the concurrency primitive can be used by all threads in the program. This is equivalent to the behavior of all concurrency primitives instead. Thread scope device indicates the concurrency primitive can be used by all threads on the same processor. For example, all threads on a GPU or all threads on a CPU. Thread scope block indicates the concurrency primitive can be used by all threads in a CUDA thread block. Thread scope thread indicates that the concurrency primitive can only be used by a single thread. This one may seem counterintuitive, but it's actually quite useful. Thread scope thread can be used to express a concurrency primitive that doesn't actually do any synchronization. This is helpful if you want to call an interface that expects a concurrency primitive, but you don't actually need synchronization, and thus you'd like to avoid paying for it. Additionally, modern NVIDIA GPUs have asynchronous instructions that need to be synchronized within a single thread. Stood Atomic and CUDA Stood Atomic are strictly conforming implementations of standard C++ atomics. They are equivalent to a CUDA atomic with a thread scope of system. Now, let's look at some examples of how you'd write atomic code in CUDA before the NVIDIA C++ Standard Library. While these examples are specific to CUDA, the lessons are applicable to many other non-standard atomic APIs, like the old GCC-style sync built-ins. We'll see why C++ atomics are a much better abstraction. Imagine we have a producer thread that will write some data and then atomically store a flag to inform some consumers that the data is ready for consumption. Before standard C++ atomics, you might try to use volatile stores to set the flag. This isn't sufficient though, because volatile doesn't actually guarantee atomic semantics. It's not safe for inter-thread communication. Even if volatile happens to work on some systems, it might break in the future, and it certainly won't be portable to other platforms. Volatile is not equal to atomic. There's also a subtle bug here. We forgot to add an explicit fence. Without it, we'd have a data race if we were expecting consumers to see any writes that we made before we stored to the flag. This is unfortunate. The fence should really be fused onto the actual store operation. That would make it harder to forget and make a mistake here. What we really want is an atomic store release, not a volatile store. Unfortunately, the legacy CUDA atomics have no atomic store operation. As a hack, we could use atomic exchange instead. We still can't get rid of the fence. CUDA legacy atomics have relaxed semantics. We need the fence here to get the release semantics that we require. Here's what this code looks like using standard C++ atomics. Much simpler. One subtle improvement. We can use the correct type, bool, instead of int for our flag. Most older atomics APIs only traffic in 32-bit and 64-bit integers. Standard C++ atomics can be used with any trivially copyable type. We're just using atomic's assignment operator here. That will work, but the assignment operator, and all other atomic operator overloads, will use the strongest memory ordering, sequential consistency. We only need release semantics here, which we can get by instead calling the store method with an explicit memory order parameter. There's an even better form of this that we can write with C++20's new atomic wait and notify API, which is available in C++11 and up in the NVIDIA C++ Standard Library. After storing true to the flag, we call notify all in the atomic to wake up anyone who is waiting for the value of the atomic to change. On the consumer side, we have a function that pulls in the flag and then reads some data that the producer wrote to before signaling. Here's what it looks like without standard C++ atomics. We have the same issues with volatile here that we had before. We have a new issue too. We pull in the flag using a naive spin loop. Under contention, this is going to perform poorly. We've also got the same bug we had before. We forgot a fence. We need acquire memory semantics here to ensure we'll actually observe the write to the data from the producer. To get that, we need an explicit fence after we've seen the flag write and before we read the data. Instead of doing a volatile load of the flag, we should really be doing an atomic load acquire. But legacy CUDA atomics don't have an atomic load. The closest we can get is an atomic add with an increment of 0, which is inefficient and also just ugh. CUDA legacy atomics all have relaxed semantics, so we still need the fence to ensure we get acquire semantics. These aren't CUDA-specific problems. They're common to many other platforms pre-C++11 atomics APIs. With standard C++ atomics, this code is much cleaner and more correct. Here, we're using atomic's implicit conversion to T, which loads the value with sequentially consistent semantics. But we don't need sequential consistency here. A load acquire will suffice and be more efficient. We can get that by explicitly calling load with a memory order parameter. We still have a naive spin loop though. Under heavy contention, all the polling threads will be hammering this atomic, which will create unnecessary memory traffic and exacerbate the contention. Instead, we can use the atomic wait and notify API to wait for the value to change from false to something else. This API is new in C++20, but is available in C++11 and up in the NVIDIA C Standard Library. When you call wait, you give it a particular value. The call to wait will not return until the atomic is no longer equal to that value. If you recall from before, we called notify all on the producer side, which will inform the sleeping wait calls that it is time to check the value again. The particular waiting mechanism that is used is left up to the implementation. On a CPU, you might use an OS primitive like a futex. In our implementation for GPUs, we use a backoff mechanism that will sleep the waiting thread for a short duration after failed reads. This will reduce contention when the atomic is under load. It's difficult to write heterogeneous code with CUDA legacy atomics because they only work in device code. Atomics in the NVIDIA C Standard Library work in both host and device code. C++ atomics also give you a greater degree of type safety than you get with legacy CUDA atomics. For example, if you mix thread scopes of your atomics, C++ atomics will catch that at compile time and give you an error. However, the type safety that the standard C++ atomic class provides can sometimes be a limitation. Legacy CUDA atomics work on raw bytes, so you don't have to change the type of objects to access them atomically. You can just cast to the appropriate integer type. The standard C++ atomic class requires you to change the type of the objects you want to access atomically. That's not always possible or desirable. The objects may be defined by someone else, or changing their type would impact a ton of code or pessimize non-concurrent code. For example, imagine we have a function that counts the number of occurrences of each letter in a string. A group of threads use it to count a string in parallel. Each thread works on a different chunk of the string, but uses the same bins array for counting. Two different threads may increment the same bin at the same time, so synchronization is required. But it may be impractical for us to change the bins to be an array of atomic ints instead of an array of ints. That would require existing users to change their code, and it may pessimize later uses of the bins array that do not require synchronization. Fortunately, C++20 has introduced a remedy for this problem, atomic ref. While atomic of t holds a t internally, atomic ref of t doesn't hold the t. It instead holds a reference to a T. You construct an atomic ref which points to an existing object, and then by accessing that object through the atomic ref, you get atomicity. Atomic ref has the same syntax and semantics as atomic. It also has the same requirements on T as atomic. The type must be trivially copyable. We can use atomic ref in the places where we need to treat an object as atomic, but can't change the type of the object. All concurrent accesses to the object must happen through an atomic ref. Using atomic ref will not make non-atomic accesses atomic. Just like atomic, we have two versions of atomic ref in the NVIDIA C Standard Library, an extended version in CUDA, which takes an optional thread scope parameter, and strictly conforming versions in STUD and CUDA STUD, which are equivalent to a CUDA atomic ref with a thread scope of system. Atomic ref will be available soon for C++ 11 and up in the NVIDIA C++ Standard Library. I want to encourage everyone to stop using legacy CUDA atomics. They have a number of problems. There's no direct way to express sequential consistency and acquire release semantics. You have to build them yourselves using fences. They're device only. Memory scope is a property of operations, not objects. Likewise, atomicity is a property of operations, not objects. C++'s atomic and atomic ref classes are complete replacement for legacy CUDA atomics, which are more expressive, more correct, and less error-prone. And please stop using volatile for synchronization. It is not correct. Volatile is not guaranteed to either work or be performant for synchronization. Even if it happens to work today on some platforms, you should switch to C++ atomics now to avoid surprises from future compiler or hardware changes. Volatile does not give you atomicity. To learn more about atomics, check out Georgie's GTC talk, where he'll explain how the C++ memory model works and show you how to develop concurrent algorithms for GPUs with atomics. Now let's talk about barriers in asynchronous data movement. C++ 20 introduced a new barrier concurrency primitive with an asynchronous arrive wait interface. It's available in C++ 11 and up in the NVIDIA C++ Standard Library. When you call arrive, you signal that you are at the next phase of the barrier, but you don't wait until that phase completes. Instead, arrive will return immediately and give you back a token which can be waited on later. You can block on the token by calling wait. The token is single shot. You can only call wait on it once. There's also a more traditional arrive and wait method, which will arrive on the barrier and wait for the phase to complete. Standard C++'s barrier is a modern replacement for sync threads. Sync threads only works in device code and only within blocks. You have no control over granularity with sync threads. It only synchronizes all the threads in a block. What if you need multiple barriers? What if you only want some threads to participate in a barrier? What if you want to synchronize across blocks? What if you want to synchronize with the host? Standard C++'s barrier is the answer. Our implementation works across your entire system, across host and device threads. With C++'s barrier, you can control which threads synchronize on which barriers. Let's look at a more advanced example, a 1D 3-point tiled stencil solver. Each thread will solve a tile of points from index I to index j. The tile is stored in fast local memory. A global array in slower memory will store the initial state and final result. Transfer to and from the local tile and global array is done before and after solve is called, except for boundary points between tiles, which are updated at each time step. At the start of each time step, we load from the global array the points that we need from our neighbors. Then we solve the interior region, the points whose stencil falls entirely within the tile. Next, we do async threads. We want to make sure everyone has read their neighbor points from the global array before we overwrite them with points for the next time step. Then, using our neighbor points, we solve our boundary points and store the results in the global array. Finally, we sync threads again to make sure everyone sees the new boundary points before they start reading them in the next time step. This isn't as efficient as we'd like. Every thread must wait for every other thread to read its neighbor points and solve its interior region before it can start storing to the global array. We only need to wait for all other threads to read their neighbor points before storing. We shouldn't have to wait for them to solve their interior region. We could remedy this by moving the first sync threads before the solve of the interior region. But then we won't be able to start solving the interior region until everyone has read their neighbor points. Instead of sync threads, we should be using a barrier from the NVIDIA C Standard Library. Remember, with a standard C barrier, we can asynchronously arrive at a barrier and then later wait on it. That's exactly what we want here. Instead of doing a blocking sync threads before the solve of the interior region, we just asynchronously arrive on the barrier to indicate that we've read our neighbor points and that they can now be overwritten. After the solve of the interior region, we wait on the token that we got from the asynchronous arrival to ensure that everyone has read their neighbor points before we write the new neighbor points for the next time step. But we've still got an inefficiency here. We're synchronously reading from the global array in slower memory. Instead, we could use the CUDA memcopy async extension to overlap these reads with the solve of the interior region, which does not depend on them. Memcopy async works just like memcopy, except that it has not necessarily completed when the function returns. It takes an additional barrier parameter, which the memcopy async operation will be associated with. To wait for completion of the memcopy async operation, just wait on the barrier. We can also switch our writes back to the global array to use memcopy async. This pattern may be familiar to those who have used non-blocking MPI. You can also use CUDA pipeline, another one of our extensions, to do more advanced orchestration of asynchronous operations like memcopy async. If you want to learn more about it, there's another GTC talk that will go into all the details. We've been talking a lot about our concurrency features, and I want to explain why we believe they're so important. Modern NVIDIA GPUs implement C++ parallel forward progress guarantees and the C++ memory model. Why did we invest in these capabilities? Why does this matter? The answer is that these capabilities enable a wide range of concurrent algorithms and data structures that were previously unavailable on GPUs. Let's take a look at the taxonomy of concurrent algorithms. On platforms that only ensure that threads make weakly parallel forward progress, you can only use non-blocking algorithms. Such platforms include all non-NVIDIA GPUs and NVIDIA GPUs prior to Volta. This greatly restricts the type of concurrent code we can write on those platforms. For example, the simple atomic polling function we looked at before cannot be used on these platforms because that function used blocking synchronization. But on Volta and newer NVIDIA GPUs, you have parallel forward progress guarantees, which means you can write any type of concurrent algorithm. More concurrent algorithms and data structures means more code can run on modern NVIDIA GPUs. Now let's look at a more detailed example, a concurrent GPU-friendly hash map. We'll use open addressing and linear probing, both for simplicity and performance. The number of slots in the map are fixed. We don't dynamically grow the map. When we run out of slots, insertions will fail. Keys are stored in one array, and values are stored in another array. Each slot has a state, which is updated atomically. The state of each slot transitions from empty to reserved to filled. No other transitions are allowed. Once a slot has become filled, it can never change to another state. We have a function object for hashing keys, and another one for comparing keys for equality. Now let's look at the concurrent insertion algorithm. When inserting, the first thing we try to do is lock our candidate slot. To do that, we attempt to set the slot to reserved. There are three possible outcomes. If we succeed in setting the slot to reserved, the insertion will succeed. So we fill the slot with the key and value, and then set the slot to filled to unlock it and allow others to read it. If we try to set the slot to reserved and the slot is already filled, then either we're inserting a key that already exists, or this is a collision. To determine which situation we're in, we check if the key in the slot is equal to our key. If it is, then there's already an element with our key in the map, so insertion has failed. If the key in the slot is not equal to our key, then this was a collision. That means we need to move on. We find the next candidate slot for our key and start the whole process over. Finally, if we're trying to set a slot to reserved and we find it's already reserved, then someone else has locked it, but they haven't finished the insertion yet. We need to wait until they unlock it by filling it, so we can figure out if the slot has the same key as us, meaning our insertion would fail, or if this is just a collision. Now let's dive into the code. The first thing we do in the insertion method is compute the first slot we should attempt to put the specified key in. We do this by hashing the key and moduloing the result with the capacity of the map. Next, we'll enter a loop where we iteratively try to insert the key into a slot, and if that fails, pick another slot and try again. If we fail to find any slots after making a number of attempts equal to the size of the container, we give up because we've tried every slot in the map and failed every time. Let's look inside that probing loop now. The first thing we do is atomically load the state of the slot that we're probing. If that state is empty, then we're going to try and lock the slot for ourselves. To lock a slot, we need to set its state from empty to reserved. We try to do this with a compare and exchange, a CAS. We use acquire release semantics here. If someone else has succeeded in inserting in the slot, we want to make sure that we see the key and value that they wrote before they updated the state. If our CAS succeeds, then we've set the state to reserved and have acquired the lock. In that case, our insertion will succeed. So next, we insert the key and value. After that's done, we set the state to filled to unlock the slot and signal to other threads that it can now be read. Notice that we use memory order release on the store here. We want to ensure that if another thread reads the state as filled, they will also see the insertion of the key and value that happened before the store. Finally, we need to wake up any threads that may have been waiting on this slot. We do this with notify all. Then we're done. We return a pointer to the inserted value. Now, if we failed to set the slot to reserved, but we've observed that the state of the slot is now reserved, that means another thread has acquired the lock and we need to wait for it to fill the slot. We'll know the slot is ready to be checked when its state changes from reserved to filled. We could check for this with a naive spin loop, but this won't perform very well under contention. Instead, we can use atomic wait. This essentially says, wait until the state is no longer equal to reserved. If a slot is in the reserved state, it can only change to one other state, filled. So once this wait returns, we know the slot is filled. Once the slot has been filled by the other thread, we need to check if the key is the same as our key. If it is the same key, then the insertion failed, and we just return a pointer to the value the other thread inserted. Otherwise, this is a collision. So we try again with the next consecutive slot. And that's it, an efficient and GPU-friendly implementation of concurrent insertion into a hash map. I'm not going to show you the algorithm for lookup today. It's a bit simpler, and it uses the same basic principles. And it's not just hash maps. There's a whole new world of algorithms and data structures that can be accelerated with modern NVIDIA GPUs using the NVIDIA C Standard Library. If you want to learn more about concurrent hash maps and other GPU-friendly data structures, check out our Coup Collections library. To build data structures, you'll need other tools as well, like memory resources and allocators for different kinds of heterogeneous memory. I'm pleased to announce that those will be added to the NVIDIA C Standard Library in an upcoming release. Our heterogeneous memory management layer is an extended version of standard C++'s memory resource and allocator framework. First, we have heterogeneous memory resources. Memory resources are stateful memory allocation classes. CUDA memory resource works just like std PMR memory resource, except it takes an additional memory kind parameter. Likewise, CUDA allocator works just like std PMR allocator, except it takes an additional memory kind parameter. It's a typed, cheap handle to a memory resource. In standard C++, memory is flat, uniform, and interchangeable. But in reality, on heterogeneous systems, there are many different classes of memory. So, we've introduced a notion of memory kinds so that interfaces can express what kind of memory they require. We're also adding asynchronous memory resources and allocators that are built using CUDA-malloc async. Because of their asynchronous nature, these facilities will have slightly different interfaces than their standard C++ counterparts. As part of the asynchronous memory resource and allocator API, we're also adding CUDA Stream View. This is our first modern C++ API wrapper for the CUDA runtime. We expect we'll add many more in the future. CUDA Stream View is very simple. It's just a non-owning wrapper around a CUDA Stream T. Finally, let's look at the future of parallelism in standard C++. There are three key components to C++ standard parallelism. A corpus of common parallel algorithms, such as the C++17 parallel sequence algorithms, which have a standard interface but are implemented under the hood by vendor-optimized parallel libraries. Tools like executors, atomics, and concurrency primitives that enable you to write your own parallel algorithms that can run anywhere. Mechanisms for composing parallel invocations into asynchronous task graphs, such as ranges and senders. C++17 introduced parallel versions of the C++ sequence algorithms. They're powerful, but they have some limitations. They're iterator-centric, not index-centric. Also, they aren't really composable. Fortunately, ranges can be used in conjunction with the parallel algorithms to iterate over indices, including multidimensional indices, and to compose together algorithms and do kernel fusion. Ranges were introduced in C++20, and we're working on bringing them to the NVIDIA C Standard Library. Suppose we want to iterate over a sequence of indices instead of a sequence of elements with a thrust or standard C++ algorithm. In thrust, we'd use counting iterators for this, which will synthesize the indices when they are dereferenced. In standard C++, we'd use ranges. A range is a sequence of elements. A view is a range that is cheap to construct, move, and copy. You can get a begin and end iterator from ranges and views. For example, std vector is a range. It owns its data, and you can get a begin and end iterator to it. Std span is a view. It doesn't own the data it refers to. It's just a pointer into size. Range factories produce ranges that synthesize data on the fly. In C++20, we can use the iota range factory to produce a range that iterates over indices. We can get a begin and end iterator from the range and plug it into C++ parallel algorithms. Neither thrust counting iterator nor iota ranges create any storage for the index sequence. The iterators store a count, and each time they are incremented, they increase the count. When they are dereferenced, they return the count. This gives us an elegant way to do index-based iteration with C++ standard parallel algorithms. Ranges work with iterator-based algorithms like the C++17 parallel algorithms, but they're most natural with the new range-based algorithms in C++20, which take ranges instead of iterator pairs. We don't have parallel versions of the C++20 range-based algorithms yet, but we're planning to add them in a future standard. We can also use ranges to do multidimensional iteration using range adapters. Range adapters are higher-order constructs that take one or more ranges as an input and produce a range that transforms or reinterprets the underlying ranges in some way. The Cartesian product range adapter produces ranges that iterate over all combinations of elements from a set of underlying ranges. For example, calling the Cartesian product range adapter with two iota ranges, one from 0 to n and one from 0 to m, will produce a range of all two-element tuples from 0, 0 to nm. As shown here, this lets us express multidimensional iteration, like a matrix transpose operation. Cartesian product should be coming in C++23, but it will be available in the NVIDIA C++ Standard Library before then. Range adapters can also be used to compose together different algorithms. The C++20 transform range adapter takes a sequence of elements and a function as an input. When iterated, it returns the result of applying the function to the underlying elements. It works just like Thrust's transform iterator. This composition is very powerful as it allows you to construct more complex algorithms. For example, our parallel implementation of the transform reduce algorithm simply calls the reduce algorithm with a transform range. Here's a more advanced example with transform ranges, where we consecutively invoke three different kernel functions, f, g, and h. In the standard C++ example at the right, we fuse all three into a single kernel launch. Notice that we use the pipe operator here. All range adapters support this. The pipe operator is used in ranges to build up partially applied lazy sequences. It works very similarly to pipes in shell scripts. The output from the left-hand side of the pipe is fed into the right-hand side of the pipe. We also want to expand beyond one-dimensional sequence algorithms. The C++ committee is working on introducing C++ linear algebra algorithms and array types that abstract the BLAs. Under the hood, these interfaces would connect to accelerated vendor libraries like cuBLAS and cuTensor and utilize hardware like NVIDIA tensor cores. The C++ committee is also developing executors, a framework for orchestrating parallel execution and writing your own portable parallel algorithms. This framework will provide portable and unified abstractions for parallelism, asynchrony, concurrency, and I/O. Executors will unify work launch across different targets and programming models. For example, it will provide one unified way to launch work on a thread pool, on a fiber, with OpenMP, or using any of CUDA's various launch mechanisms, regular launch, cooperative grid launch, or graph launch. Executors support both lazy and eager execution models. With executors, you can express execution dependencies and compose together asynchronous task graphs in standard C++. Executors will be coming in a future C++ standard, but we plan to have them in the NVIDIA C++ Standard Library before then. Now, let's go over some of the key constructs and components of the executors framework. Executors parameterize execution resources, allowing us to write code that can run anywhere. Executors are to execution what allocators are to allocation. Senders represent asynchronous work that will be ready later. They're a generalization of things like stood future. Sender factories and adapters are the basic building blocks of task graphs. Sender factories are functions that synthesize new senders. For example, schedule is a sender factory that takes an executor and produces a new chain of work on that executor. Sender adapters are functions that take predecessor senders and produce new senders that depend on the predecessors. For example, bulk is a sender adapter that takes a sender, a shape, and a function. It executes the function on a set of execution agents described by the shape after the predecessor sender has completed. If the predecessor sender has a value, it gets sent to all of the function invocations. Here are some other common sender factories and adapters which aren't used in this example. Just takes a value and returns a sender that will send that value to its successor. Then is a serial version of bulk. It's a sender adapter that takes a sender and a function. It executes the function on a single execution agent after the predecessor sender has completed. If the predecessor sender has a value, it gets sent to the function invocation. On switches the executor that the chain is using. It takes an executor and returns a sender that will propagate that executor to its successors. Sender adapters are pipeable, just like range adapters. The expression on the right-hand side of a pipe is a partially applied sender adapter. It produces a new sender that depends on the sender on the left-hand side of the pipe. The semantics of the pipe operator for sender adapters are very similar to pipes and shell scripts. That's our roadmap for C++ standard parallelism. We think it's a very compelling story for parallel programming. Write your code once using standard facilities and run it anywhere. That's all for today. The NVIDIA C++ Standard Library, a standard library for your entire system. You can get it today on GitHub, in the NVIDIA HPC SDK, and in the CUDA toolkit. If you want to learn more about standard C++, CUDA C++, and the NVIDIA HPC SDK and compiler, be sure to check out these talks, blog posts, and other resources. I want to thank my excellent team who made all of this possible. I also want to thank you for your time. I hope you have a wonderful day.